Hi, I'm going to give a few tutorials on matrix algebra and calculus, and this is designed to catch people up in calculus and matrix algebra. I know we're doing a lot with all this taking inverses of covariance matrices and finding optimal portfolios. So if you didn't have 501 or if you've kind of forgotten about it, go through these videos. This will be a multi-part video on matrix algebra followed by calculus and some other things. All right, so I get this, the basic gist of this from the calculus and matrix problems and solution sets in the MSF 504 file on the Google Drive. So we click this and it's the material covered in this paper right here. It's about 40 pages, and I know it's a lot to cover, but let's see if I can make any sense of this. Okay, so what we're doing is we're trying to solve a series of simultaneous equations. So if we have two unknowns, x, y, and two equations, in many cases we can solve this. Not always, but we can always solve this by, I don't know, maybe multiply the top by -2, the bottom by 3, the bottom line by 3, do some substitution, and what we end up with is x equals, let's see, -3, and y equals 6. So if we plug that in there, oh yeah, it works. So that would be a -6 right there. 6 times 3 is +18. All right, so that works. It works for both. And really all it is an intersection of these two lines. So the solution to a series or a set of simultaneous equations is a point where they all intersect. All right, so not every simultaneous equation is as easy as that. This is a hard one. We have 5 equations and 5 unknowns. So we have x1 through x5. And we have 5 equations, and doing a lot of substituting here would be kind of a pain. But thank goodness we have some some Excel and R type problems or solutions to this problem. All right, so not every set of equations have solutions, or much less, or at least unique solutions. So if we have 2x plus 3y equals 12, or 2x plus 3y equals 2. Wow, we have the same coefficients on the variables, but they equal 2 different things. So what we have right here are these two lines are parallel. All right, so we're looking for points where lines intersect. Well, if they're parallel, they'll never intersect. So there's no solution here. And incidentally, if this was, let's say, 4x plus 6y equals 4, well, really, that's the same as this equation. They're identical equations because we can divide both sides by 2, and we get this equation up here, which is an example of what we have in the next slide. So we have 2x plus 3y equals 12, and 4x plus 6y equals 24. It just happens that the second line equals first line times 2. And so basically, this is the same equation stated in superficially different ways. And so the intersection of both of these equations is, well, it's the same darn line. So there's an infinite number of solutions. So it goes from -infinity up to +infinity for x. So there is no unique solution here. All right, so let's take a look at some matrix mathematics. So what a matrix is a rectangular set of numbers or coefficients. And if we add two matrices, oh, for instance, let's just put this one, 3, 2, 1, 1, 4, 0. All right, so if we're going to add one matrix, call this matrix A, with another matrix, they have to have the same dimension. So the dimension is number of rows by number of columns. All right, so there's 3 rows here and 2 columns. So if we add a matrix A and B, the second matrix also has to have 3 rows and 2 columns. So -1, 0, 8, 4, 2, -1. All right, so when we do some matrix addition, what we do is cell by cell addition. So it's that first row, first column by first row, first column, and we get the sum of first row, first column. So we get, well, sorry about that. We get 3 plus -1 is 2, 1 plus 4 is 5, 2 plus 0 is 2, 4 plus 2 is 6, 1 plus 8 is 9, and 0 plus -1 is 0. -1. So that's how we can add these matrices. And what a scalar is just a number. You know, it's a magnitude. All right, so what do I mean by this? Well, let's say we have this matrix A, 3, 2, 1, 1, 4, 0. And if we multiply it by some scalar, let's say 4, what this does is it telescopes everything up in A by a magnitude of 4, by a factor of 4. So it'll be 4 times 3 is 12, 4 times 2 is 8, 4 times 1 is 4, 4 times 1 is 4, 4 times 4 is 16, and 4 times 0 is 0. Right, so that's scalar multiplication. And now we're going to look at the matrix multiplication, which is the most useful. So let's say we have A. What we have is 3, 2, 1, 1, 4, 0. So this is a 3 by 2 matrix. And let's see, we got 1, 2, 3, 4. That's not right. So 1, 2, 3, 4 is 0, 1. Let me just go back to what I wanted. So what do we have here? We have a 2 by 2 matrix. And so what we need when we do matrices, we need to have matching number of columns in the first matrix. And let's say this is matrix C. And we have to have the matching number of rows. And we'll see why here. So if we have A times C, what we do is we do row times column sum products. So we have 3 times 1 plus 2, 1 times 2. And so what we end up with, we're going to end up with a 3 by 2 matrix, the first set of columns and the first set of rows and the last set of columns. And so what do we have here? So we have first row, first column is 5. First row, second column is 3 times 3 plus 1 times 4. So that's 9 plus 4 is 13. Then we have second row, first column, 2 plus 8 is 10. Second row, second column, 6 plus 16 is 22. And then we have third row, first column, 1 times 1 plus 0 times 2 is going to be 1. And we have third row, second column, and that'll be 3. All right, so the way we can do this in Excel is with the matrix multiplication formula. M mult, and then we have array 1, which is the A, and then array 2, which is the B. And so again, what we have to have is matching columns in the first matrix and matching rows in the second, and the dimension of the matrix when we're all said and done is going to be the rows of the first times the columns of the second. All right, we'll stop right there to keep these notes short, because if you know this stuff, just get out, stop, and by the way, play this at double speed because this is kind of dry material. All right, talk to you later.